Hello again. This is section 8.3, polar form of complex numbers and de Moivre's theorem. So in this section, we're going to take a look at complex numbers. If you remember back to your pre-calculus, complex numbers are numbers that have a real part and an imaginary part. We're going to look at how we can actually plot those in a complex plane and then also find the polar form of those complex numbers. Then we're going to look at de Moivre's theorem, which allows us to actually find higher powers of some of these complex numbers, but in an easier way by using the polar form of those complex numbers. So we're going to start here by looking at the complex plane. So if you notice, it looks very similar to an X and Y coordinate system. It's just that our horizontal axis now represents the real part of a complex number. The vertical axis is going to represent the imaginary part. And so if our real part is positive, we go to the right. And if our real part is negative, we go to the left. And if our imaginary part is positive, it goes up. If our imaginary part is negative, it goes down. But we're basically plotting these points like we would an X and Y coordinate. We're just looking at a real part and an imaginary part of a single complex number now, rather than an X and a Y coordinate. All right, so our first example, we want to actually graph these complex numbers. So our first one that's given is 2 plus 3i. So I'm going to draw my vertical and horizontal axes. So remember, the vertical gives us the imaginary part, and then our horizontal is the real. Our real part this time is 2, so that tells us we're going to go over 2. It's positive 2, so we're going to the right. And then our imaginary part is a positive 3, so we're going to go up 3 on the imaginary axis. And so we're going to end up with a point right here at 2 plus 3i. All right, now the next one. Same thing, we have our real axis and our imaginary axis. This time we have 3 minus 2i, so our real part is positive 3, so it's still going to go to the right. This time, though, our imaginary part is negative 2, so we're going to go down 2 units. So this time we end up with a point right down here. This is going to be 3 minus 2i. All right, and then finally we want to graph z1 plus z2. So the first thing we've got to do is actually find the value of z1 plus z2. So I'm going to do that first. We have z1 plus z2. When I add two complex numbers, I'm adding the real parts, I'm adding the imaginary parts. So if I add the real parts together, 3 plus 2 is going to give us 5. And when I add the imaginary parts, we have a positive 3i, a negative 2i. It's going to give us a positive 1i. So now we're graphing the point 5 plus I. And we have our real axis and our imaginary axis. This time our real part is positive 5, so we're going to go to the right 5. And our imaginary part is a positive 1, so we go up 1. And we have this point right here. So this represents z1 plus z2, because that's the point that we get once we add those two complex numbers together. All right, now the next example says we want to graph each set of complex numbers. So the first one is a plus bi, that's just any complex number. And then this vertical line right here, we read as such that. Okay, so whenever you see that, we're reading a plus bi such that the a value is greater than or equal to 0. So we want to think about in our complex plane now, where the horizontal axis is the real axis, the vertical is the imaginary, where would all the complex numbers be whose a value is greater than or equal to 0? Okay, so that means the real part has to be greater than or equal to 0, meaning we have a positive real part. The imaginary part, though, could be anything, and so that ends up being everything to the right of that vertical axis. Okay, so we're looking at shading everything over here now, because we're saying that the real part has to be positive, but the imaginary part could be anything. All right, now the next one, we're looking at all of the complex numbers, a plus bi, such that a is less than 1, so the real part has to be less than 1, and b, the imaginary part, has to be greater than or equal to 0. So again, I'm going to draw my real and imaginary axis. This time, I want the real part to be less than 1. So what I'm going to do is I'm going to put a value at 1. And since it's strictly less than, not less than or equal to, I'm going to use a dotted line at 1 this time. Okay, so here's A equals 1 right here. B, the imaginary part, needs to be greater than or equal to 0, meaning we need a positive imaginary part. So we're basically shading everything to the left of 1 along the real axis and everything above the real axis in the imaginary, since we want the imaginary part to be greater than or equal to 0. And so that's basically going to give us everything up here now. So everything that's less than 1 along the real axis, but also greater than or equal to 0 along the imaginary axis is going to give us that shaded region there. All right, now the modulus of a number, okay? So the modulus or absolute value, right? Those two things mean the same thing, of a complex number is going to be the square root of a squared plus b squared. So we take the real part, we square it, we take the imaginary part, we square it, we take the square root of that sum, and that's going to give us our modulus or our absolute value of a complex number now. Now remember, an absolute value just tells you the distance a number is away from 0. So that's exactly what we're finding here when we're looking at a modulus. We're asking ourselves, how far away from 0, from the origin of our complex plane, is this complex number? Okay, and that's why we're using square root of a squared plus b squared. It's basically like Pythagorean theorem. It's giving us now that distance from the origin. All right, so we want to find the moduli of the complex numbers 3 plus 4i and 8 minus 5i. So moduli, just the plural form of modulus. Okay, so we're looking for a modulus for both of these. So let's start with 3 plus 4i. So if I look for the modulus of 3 plus 4i, remember our formula is square root of a squared plus b squared. Well, the a value this time is 3, so 3 squared, plus, and then the b value is just the number in front of the I, so that's just going to be 4 squared. And how we simplify, 3 squared is 9, 4 squared is 16. Adding those together, we get the square root of 25, and the square root of 25 should give us 5. And so our absolute value or modulus of 3 plus 4i is just equal to 5. Okay. Now we'll do modulus of 8 minus 5i. Again, formula square root. A squared is going to give us 8 squared plus, and then our b value this time is negative 5, so we get negative 5 squared. Squaring each of those now, 8 squared is 64, 5 squared is 25, and if I add those together, we get 64 plus 25 is 89. Now, square root of 89, not a perfect square. Also, no perfect squares that go into 89, and so the square root of 89 is as simple as that answer is going to get. All right, so now we're graphing a set of complex numbers. So we want the set of complex numbers such that the modulus of the complex number is equal to 1. Okay, and remember, we just said the modulus is like the absolute value. It's the distance away from 0. So if I sketch this, we have our real axis and our imaginary axis. If the modulus is 1, that means that we want all the points whose distance is 1 away from the origin. So basically, we're going to go out 1 unit in all directions here, right? So this would be negative 1 over here, negative 1 down here. Okay, but in all of those cases, we're exactly 1 unit away from the origin. Now, if I want every single point whose modulus is 1, what I'm going to have to do is draw a circle. So we end up with a circle that goes through all of those points there, because every single point along that circle now would have a radius of 1, so the distance away from the origin now is always going to be 1. now the second one, we're looking for all the complex numbers such that the modulus is less than or equal to 1. Well, we just looked at where it would be equal to 1, so we know that's going to be part of our graph. So I'm going to go ahead and start with that. So I'm going to have my 1, negative 1, negative 1, and 1. And we've got our circle, goes through all of those points. Now, if I want to be less than or equal to 1, that means I want all the points whose modulus, whose distance away from the origin, is less than or equal to 1. Well, if I want my distance to be less than 1, I'm looking at all the points that are inside that circle now, because every single point inside here would have a distance away from 0 that is either 1 or less than 1. And so we end up with this circle with a radius of 1, and then all the points inside the circle end up shaded. All right, now the polar form of complex numbers. So this is how the polar form is going to come in. If we're looking for the polar form, we're going to use this equation here that z is equal to r times the cosine of theta plus I times the sine of theta. So we're taking the r value, which is just the modulus of z. Because if you think about that circle that we just looked at, the radius of that circle was also the modulus. And so we're saying the modulus now gives us the r value. And then we can use our tangent function to say tangent of theta is equal to b over a. So just like tangent was y over x before, now it's going to be the b value of the a value, because the b is the vertical axis, the a is the horizontal axis. And so we can use our tangent function to help us find the theta value. Okay. Once we know theta and we know our r value, then we just plug them into that z equation, and that's going to give us our polar form of a complex number. All right, so let's see if we can write each one of these in its polar form. So we've got 1 plus I. First thing we need to do is find the r value. So remember, the r is just the modulus, so that's going to be the square root. Our a value this time is 1, so we get 1 squared. Our b value also 1, so 1 squared. That gives us the square root of 1 plus 1, which is just the square root of 2. All right. Now we need to find our theta. So we take tangent theta equals, remember it's going to be b over a, so the imaginary part over the real part. So it's going to be 1 over 1. It tells us tangent theta has to be equal to 1. And now we can do our inverse. So we do the inverse tangent of 1. And so the two places that tangent could be positive 1 would be either in the first quadrant or the third quadrant, because those are the two quadrants where tangent would be positive. Now notice this time, our original point, 1 plus I, because the real part and the imaginary part are both positive, that means that we're going to be in the first quadrant. So I only have to worry about the theta value that's in the first quadrant this time. Well, the one where tangent would be equal to 1 would be pi over 4. So again, even though we technically could have a value of pi over 4 or 5 pi over 4, first or third quadrant, because the original point, 1 plus I, both values are positive, that puts us in the first quadrant. That's why it has to be the pi over 4. And now that we have all the values, now we can put it into our form. So we get z equals, we start with the r value, so that's square root of 2, times cosine of our theta value, pi over 4, plus I times the sine of our theta value, which again is pi over 4. And that's all we want to do there, okay? Because if we were to actually simplify and calculate the cosine of pi over 4, the sine of pi over 4, distribute the square root of 2, all that's going to happen is it's going to give us back the original complex number that we started with. Okay, and so this is now the polar form of that complex number. so let's try the next one. So this time, again, we want to find our r value. So we have square root. Our real part this time is -1, so -1 squared, plus imaginary part is square root of 3, and we got to square that. Well, -1 squared is 1. Square root of 3 squared is 3. We end up with square root of 4, which is just 2 this time. Now we'll find our theta value. So tangent of theta equals b square root of 3 over a -1. So we get tangent theta equals negative square root of 3. Again, we're going to do our inverse tangent. So we're asking ourselves, where is the tangent value negative square root of 3? Okay. And remember, our two options here, since tangent is negative, would be either the second quadrant or the fourth quadrant. In this case, though, the original point, -1 plus 3i, the real part is negative, the imaginary part is positive. That puts us in the second quadrant. So we want to make sure we're finding the theta value in the second quadrant, which is actually going to be 2 pi over 3 this time. Now, once we have all the pieces, now we plug into our formula. So we've got z equals, start with your r value, 2, times cosine of 2 pi over 3, plus I times the sine of 2 pi over 3. All right, now the third one here, we've got -4 square root of 3 minus 4i. And we need to find our r value first. So r equals square root. This time we've got -4 square root of 3 squared plus -4 squared. Now, if I square those, -4 square root of 3 becomes 16 times 3, that's 48. So we get the square root of 48 plus -4 squared is 16. That's going to give us the square root of 64. And the square root of 64 is 8. And now we find our theta value. So tangent of theta equals b over a. So that's -4 over -4 square root of 3. Tangent theta equals, the -4's cancel here. So we end up with 1 over square root of 3. I'll write it right here. But if we were to rationalize that value, we get square root of 3 over 3. And the only reason I write it that way is because that value is probably a little more familiar to us. If you want to leave it as 1 over square root of 3, that's perfectly fine. Now we're going to take our inverse of square root of 3 over 3. And since it's positive, we're either in the first or the third quadrant. In this case, though, because the real and imaginary parts of our original number were both negative, that's going to put us in the third quadrant. So our answer here is going to be 7 pi over 6. Now we come over here, write this out. So z is equal to, our r value was 8, cosine of 7 pi over 6, plus I times the sine of 7 pi over 6. All right, and then finally we've got 3 plus 4i. Again, let's find our r value first. That's going to be square root of 3 squared plus 4 squared. Square root of 9 plus 16. 25, and the square root of 25 should give us 5 this time. All right, now we'll find our theta. So tangent theta equals, b is 4, a is 3, so we get 4 thirds. So theta is equal to the inverse tangent of 4/3. Now, 4/3 is not a special value, right? There isn't a 4/3 that we know from our unit circle. And so if we do this, we would have to put it in the calculator to get an approximate value of theta, or if you want an exact value, we have to leave inverse tangent of 4/3 as the exact value. Okay, so when I substitute this in this time, our complex number in polar form is going to look like this. Our R value is 5. We're going to have cosine of the theta value, which is inverse tangent of 4/3, plus I times the sine of the theta value, which again is inverse tangent of 4/3. And so that right there would be the exact value of the polar form for that complex number. If you don't need an exact value, if you're allowed to round, then put inverse tangent of 4/3 in your calculator, get an approximation for that angle, and then you can just put that in there. But in this case, if we're not told to round, we need values. The only exact value we can use for that angle is inverse tangent of 4/3. All right, and then the Moivre's theorem. So if z is that complex number in polar form, then z to the n is going to be this formula here. So we're going to raise the r value to the same n power, and then we're going to multiply the theta value inside by that n value. Okay, so z to the n equals r to the n times cosine of n times theta plus I times sine of n times theta. So again, the first thing we're going to have to find is the r and the theta values. Once we know those, we have our z. Once we want to raise that to the n power, we're going to take the r value, raise it to the n power, multiply the theta by the n, and that's going to give us whatever z to the n is equal to. So this time we've got 1 plus 1/2 I raised to the 10th power. So again, first thing we've got to do is figure out what is 1/2 plus 1/2 I equal to in polar form. So let's figure out the polar form first, then we'll use de Moivre's theorem to figure out what that would be to the 10th power. So I need to find my r. We got square root. Our a value is 1/2 squared. B value is also 1/2, and we square that. 1/2 squared is 1/4. So we have 1/4 plus 1/4. That's going to give us the square root of 2/4, or 1/2. And now if we wanted to simplify this, we can actually multiply top and bottom by square root of 2 to rationalize. And that's going to give us square root of 2 over the square root of 4, which is 2. Okay, so our r value just comes out to square root of 2 over 2. All right, now we need to find our theta value. So tangent theta equals b over a, so 1/2 over 1/2. That means tangent theta is going to be equal to 1. So when we do our inverse here, we look back at the original point. Both values are positive. That means we're in the first quadrant. Inverse tangent of 1 in the first quadrant is going to give us pi over 4. And so this time our z is equal to square root of 2 over 2 times cosine of pi over 4 plus I times the sine of pi over 4. And so nothing has changed from the first problems that we were doing, right? We found the z value exactly the same way. Now we're going to use de Moivre's theorem, because what we're trying to find is z to the 10th power. Okay, that complex number raised to the 10th. So remember, de Moivre's theorem tells us we're going to take the r value, square root of 2 over 2. We're going to raise that to the 10th. And then we're going to do cosine of the n value, 10 times our theta, pi over 4, plus I times the sine of And then same thing, 10 times pi over 4. All right, so now I want to simplify this. Well, the square root of 2 raised to the 10th power, basically what's going to happen is the square root and a 2 would cancel each other out. So there's 5 left over. So this just becomes 2 to the 5th over 2 to the 10th. Okay, and we'll come back and simplify that also. Okay, the square root of 2 raised to the 10th would give us 2 to the 5th, and then 2 to the 10th is just 2 to the 10th. All right, now our cosine, we have cosine of 10 times pi over 4. If I simplify that, it would be 10 pi over 4, which would give us 5 pi over 2. So we're going to get 5 pi over 2 plus I times the sine of 5 pi over 2. All right, now my goal here is to actually find a value for 1/2 plus 1/2 I, all raised to the 10th. So I need to simplify all of this down now. Well, if I look at this first part, 2 to the 5th over 2 to the 10th is going to give us 1 over 2 to the 5th power, because I can just subtract those exponents when I'm dividing since the bases are the same. So we get 1 over 2 to the 5th. Now, cosine of 5 pi over 2. 5 pi over 2 is bigger than 2 pi, so I'm going to subtract off a 2 pi just so we can get something that we might be more familiar with from our unit circle. If I subtract 2 pi from 5 pi over 2, I'm subtracting 4 pi over 2, so I'm going to be at pi over 2 this time. And then the same thing with this. It's going to get I times the sine of pi over 2. All right, now we'll simplify. 2 to the 5th is 32, so we get 1 over 32. Cosine at pi over 2 is just 0. Sine at pi over 2 is 1, so we get I times 1. Or 1 over 32 times, and then 0 plus I times 1 is just going to be I. So we end up with 1 over 32 I. Now, just so you can understand the usefulness of this, if we didn't have de Moivre's theorem to be able to convert this into a polar form and then simplify that way, we would actually have to multiply 1/2 plus 1/2 I 10 times, right? Multiply it by itself 10 times. You'd be using FOIL over and over and over again, trying to simplify this down to get to this answer. Okay, but de Moivre's theorem allows us to convert this into a polar form, plug into our z to the 10th formula at that point, and then we can actually find our value of the original complex number to the 10th power without ever needing to actually multiply all of those binomials. All right, so that's all we've got for this section. As always, if you have any questions as you're working on homework, please do let me know, and I will see you next time.